In this lecture, we'll look at some of the different methods used for the analysis of trusses, and we'll start using the method of joints. All of these lectures are supported by separate practice tutorials. Generally, there are several methods that can be used to analyse simple trusses. We can name the following methods. Qualitative analysis. This method allows us to assess the forces in truss members qualitatively, allowing us to understand whether the members are in compression or tension. The method of joints. This method employs linear equilibrium. It represents the truss through several systems of concurrent forces. The method of sections. This method employs both linear and rotational equilibrium. It represents the truss through a system of non-concurrent forces. And the graphical method. This method describes the state of forces in a truss graphically using vector addition. In this lecture, we will be discussing the method of joints. We should first begin by discussing the sign convention. Throughout this series of lectures, we will assume that tension force is positive and compression force is negative. This is how it'll look in a truss member. The positive tension force is pulling or elongating the member, and the negative or compression force is creating the member to become shorter. Let's consider the action of a pin joint. We take a joint and attach it to a simple support. Then we attach a truss bar to this joint. The truss member can only rotate around the joint. Any other movement is restricted. As a result, the pin joint restricts movement in both horizontal and vertical directions, but it allows for rotation around the joint. This means that to keep the joint in equilibrium, translational horizontal and vertical equilibrium should be enforced, while the rotational equilibrium is automatically satisfied. Now let's consider a symmetric truss loaded by a single concentrated force in the middle. This truss is made of triangular cells and therefore is stable and in equilibrium. Since the truss is in equilibrium, any part of the truss is also in equilibrium. That is, it doesn't move, therefore all the joints are in equilibrium. The method of joints starts with finding the support reactions. A free body diagram is generated where the supports are substituted with external reaction forces, as you can see here. The reaction forces are found using three equilibrium equations. Since there are only three independent equilibrium equations, only three reaction forces can be found. Before proceeding to the solution of internal forces in the truss members should be notated for easy referencing. One of the notation techniques is based on numbering the pin joints. In this case, the truss members are notated according to the pin joints they're connected to, using an increasing order of numbers as shown in the slide. So for example, between joints 1 and 4, you can see on the slide member 1, 4. After the joints are numbered, they are separated from the bars as shown here. To keep the truss in equilibrium, it is necessary to keep every joint in equilibrium. As you can see here, joints 1, 3 and 5 are not in equilibrium. Therefore, the internal forces from the truss members should be applied on the joints. Let's now discuss how to apply the internal forces on the joints. We take a truss bar connected to joints 1 and 2, as you can see here. First, the truss bar is disconnected from the joints. Then, the internal forces are applied in such a way that after the joints are connected back to the bar, the forces should cancel each other. Therefore, a tension member will have the following arrangement of forces, where the joints are loaded by a force pointing outwards, and in the arrangement of forces in a compression member, the joints are loaded by a force pointing inwards. Let's consider the arrangement of forces between the joints and the truss member. As you can see, all the forces are on one line. It can therefore be concluded that the line of action of an internal force acting on a joint is the line connecting two joints at the end of the truss member. This is the definition of a truss member. As a result, the directions of internal forces are known in a truss member, and what is left is to find the values of forces. In a truss member not loaded along its length, the internal forces on both sides are equal, opposite, and on one line of action. Otherwise, this member is not in equilibrium. This allows us to conclude that each truss member applies the same force on both of the joints that it's connected to. The next step in the solution of a truss, using the method of joints, is to remove all the truss members. This leads to free body diagrams of each joint with external and internal forces applied. As can be seen, each joint is loaded by a concurrent system of forces. The internal forces are the unknowns. As a result, the solution of the truss is reduced to a set of simultaneous solutions of several concurrent systems of forces. In the solution of these systems, it is convenient to initially assume all truss members are in tension. This means that we assume that all internal forces are initially positive and directed away from the joints. Compression forces will be represented by negative values, which corresponds to the adopted sign convention we discussed earlier. If the direction of forces in a compression member is not updated, the compression forces attract automatically. In the notation of internal force, the first number in the subscript represents the number of the joint at which the force is applied, and the second number is the joint at which the force is directed. Since each truss member applies the same force on both of the joints it connects, the order of numbering in the notation of internal forces is not important. For convenience, it can be suggested to use increasing order in the numbering of all internal forces in a truss. Let's consider, for example, pin joint 1. Since all the forces acting on this joint intersect at one point, this system of forces is concurrent. To keep the system in equilibrium, only two conditions need to be satisfied, and this includes the sum of forces in the horizontal and vertical directions. The reaction forces and internal forces are treated as unknowns. Therefore, it is important to know whether the truss considered can be solved using the method of joints. Since only two equilibrium equations can be written for each joint, the total number of equations that can be written for a truss equals twice the number of joints. The number of unknowns in a truss equals the number of reaction forces and the number of internal forces in the truss bars. And the internal forces are found from equilibrium equations written for each joint. For the truss considered, the number of equilibrium equations equals the number of unknowns, and this means that the truss can be solved using the method of joints. The analysis procedure of the method of joints should start with generating a free body diagram of the truss and determining the support reactions from the three equilibrium conditions of the entire truss. The latter results in two translational and one rotational equilibrium equation. Next, all truss members are assumed to be in tension, which is helpful for keeping track of tension and compression. The joints are disconnected from the bars and the bars are discarded. Free body diagrams of each joint are drawn, where the external and the internal forces are applied at the joints. The solution of the internal forces starts with a selection of a joint with only two internal forces applied, because only two equilibrium equations can be written for each joint. The internal forces are found from the equilibrium equations of the sum of forces. The solution continues, working from joint to joint. In the solution, each selected joint can only have two unknown internal forces for us to be able to solve. Best practice, when possible, is to achieve only one unknown force per equilibrium equation. This way, there isn't a need to go back to previous equations to find missing unknown forces. As we start solving trusses, we will find that some truss members can be unloaded, that is, have zero force. These members can be discarded from the analysis without affecting any truss members. It would be logical to ask, why are the unloaded members needed in trusses? The unloaded members are required to provide stability to loaded members. Additionally, these members may become loaded if the loading arrangement changes. If the unloaded members are identified and discarded, the analysis of a truss can become considerably simpler. The unloaded members can be identified from the inspection of member arrangements. Let's consider two main cases. The first arrangement of bars that indicates the presence of zero force members is an unloaded corner joint connecting two truss members. Note that the bars should not be on one line, they cannot be collinear. Let's consider the corner joint shown in this slide. To show that both bars are unloaded, we will write equilibrium equations. From the sum of vertical forces, it follows that force F1 is 0. And therefore, from the sum of horizontal forces, it follows that force F2 is also 0. As a result, both bars in this corner connection are unloaded. That is, they are zero force members. Another arrangement of bars that indicates the presence of zero force members is an unloaded joint connecting three bars where two of those bars are collinear. In the example shown here, the two horizontal bars are collinear. To show that the inclined bar is unloaded, we will write the equilibrium equations. From the sum of vertical forces, it follows that F1 is 0. And from the sum of horizontal forces, it follows that F2 equals F3. So we don't know what they are, what the values are, but we know that they're equal and in opposite directions, or both of them in tension. As a result, the inclined bar in this connection is unloaded. A loaded corner joint can also have a zero force member when the external load is applied in the direction of one of the bars. This is really a subcase of case 2. In the example shown here, the external force F3 is parallel to the horizontal bar. To show that the inclined bar is unloaded, we will write the equilibrium equations. From the sum of vertical forces, it follows that F1 is 0, and from the sum of horizontal forces, it follows that F2 equals F3. As a result, the inclined bar in this corner connection is unloaded. So now we know how the method of joints works. I hope you'll join me in putting this theory into practice, solving trusses using this method. Bye for now.